Hello, and welcome to today's live session, Design and Application of a Pressure Sewer System. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. Before we get started, some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and our YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of the presentation as well as a certificate of attendance. And finally, we'd love to hear from you. We've allotted about 15 minutes of Q&A during today's session, so please make use of that feature. And if we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's presenter, Derek Latchett, Director of Engineering for E1. Derek has worked with E1 for more than 10 years and has been involved with project management, sales, pre- and post-sales support, local manufacturing support, and contract management. Derek was involved in many pressure sewer projects in Australia and New Zealand, including Mornington Peninsula, where 16,000 properties are undergoing a septic to sewer conversion. Derek, welcome and take it away.
Thank you, Rachel. Good morning, good afternoon, good evening. We have participants from all over the world coming to you live from my home office and most likely to yours. Welcome everyone, and thanks for joining today. Look, we have a lot of material to cover, so let's get started. So who is E1? E1 and pressure sewer have existed for over 50 years. We are the leaders in pressure sewers, and our headquarters is in Niskayuna, New York, approximately 2 to 3 hours north of New York City. Our facility is over 75,000 square feet, houses 140 employees. This is the manufacturing center, and all the design, engineering, manufacturing, and testing of equipment takes place. E1 is predominantly involved in pressure sewers, as we'll review in length. E1 is also involved in the energy sector to the design, engineering, and manufacture of hydrogen systems for power plants. E1 supports critical infrastructure around the world. The history of E1 begins with the development of the concept of pressure sewer systems. In the 1960s, the US EPA and the American Society of Civil Engineers were tasked with solving some challenging problems in wastewater collection systems. Through their work, the concept of a household appliance to perform the task was conceived. Engineers from General Electric were engaged to help. The same GE that manufactures jet engines, medical imaging equipment, locomotives, etc. GE also manufactures household appliances, and engineers from that department developed the first sewage grinder pump for pressure sewer systems. After the completion of that project, GE was not really interested in commercializing grinder pumps. However, engineers working on the project saw great potential for the pump and pressure sewer systems. They purchased the patents from GE and founded E1 in 1969. From those humble beginnings, E1 has become the dominant global leader in pressure sewers. E1 leads the global market that we invented, and today we have an established global installation base. Over 700,000 units manufactured and installed globally. Another way to look at that is over 2.5 million people rely on E1 every day. Many prospective users have been in likely your position, being introduced to a concept of pressure sewer. They have asked many of the questions that you have or will ask and face many of the challenges that you may be confronted with. I'm confident that by the end of the presentation, you will understand and appreciate the benefits of pressure sewer systems and the tremendous value that comes with doing business with E1 and our channel partners. So that's who we are. Now, why are we here? Fundamentally, our mission at E1 is to spread awareness of pressure sewer as an appropriate solution for wastewater collection. The key way we spread awareness is to engage all stakeholders at an early stage and discuss how the systems operate. We provide design assistance at a preliminary level to develop a budget cost, which can be evaluated against other options, because ultimately, most decisions are based around overall cost. We will discuss design recommendations and cost analysis later. E1 strives to earn the title of trusted advisor when it comes to pressure sewer. E1 leverages decades of experience to provide the solutions to simplify your most challenging problems. Not all solutions may be easy or what you want to hear, but it's this honest and transparent relationship that is the foundation for trust. Finally, we establish relationships for life with all of our customers. Our singular focus on pressure sewer necessitates that every project is successful. The reputation of E1 and pressure sewer in general is at stake. A pressure sewer system is a sewage collection system. Our job is to transport sewage from point A, which is usually the source, to point B, which is a discharge. More on that later. So let's visualize the system. At each property, there is a collection tank, which contains a grinder pump, often referred to as the grinder pump station. Wastewater flows from the property into the grinder pump station by gravity, typically your standard drainage 4-inch PVC. After being ground or macerated and pressurized by the pump, the wastewater slurry enters a pipe network. Generally, this network is installed in or adjacent to the roadway with minimal cover or burial depth, usually just below the frost line. The pipe network follows the terrain of the ground as required. There's no slope because it's pressurized. As shown, the pipe can travel uphill, downhill, across flat land. Ultimately, the pipe network terminates into an existing collection system, or like is shown here, a wastewater treatment plant. You will note on this image, there's also flat areas and areas that are adjacent to water, also common applications for pressure sewer systems. Pressure sewer systems can be a variety of sizes, from a single property to subdivisions with hundreds or even thousands of houses. Since there's no large central infrastructure, there's no large capital cost and no real need for economies of scale. Pressure sewers overcome challenges presented by a variety of terrains. It all comes down to cost, and pressure sewers will nearly always deliver best value for money. As an engineer, I believe that nothing is impossible, but I certainly believe that some things are not cost effective or are cost prohibitive. With flat terrains, sewering methods like gravity sewers end up requiring very deep installations and many intermediate lift or pump stations. Large pump stations are expensive, and deep excavations can be expensive and dangerous, with trench shielding, sheet piling, etc., often required. Pressure sewers can solve those problems. In wet areas, installing that gravity system, or a vacuum system for that matter, with open cut trenching, the same cost issues with deep excavations can be magnified when we introduce the need for dewatering. Pressure sewers can solve those problems, and pressure sewers are commonly found in wet and coastal areas. Rocky terrain is expensive to excavate and requires drilling, blasting, jackhammering, etc. to install that gravity system. Pressure sewer again solve those problems, and horizontal directional drilling is often used for installation. Finally, hilly terrain means many and major pump stations at the bottom of the hill. Pressure sewer systems can, as we say, defy gravity and enable development and sewering of many hilly areas. There are three basic categories for pressure sewer projects. First are projects where existing on-site treatment or holding tanks, like septic tanks or cesspools, are no longer functional. This could be due to breakdown of the structure or changes in the environment. Pressure sewers are often used as a cost-effective means to allow a municipality or authority to eliminate these failing systems. The other large segment of the market is new land development. Pressure sewers will be shown to provide land developers with the opportunity to cost-effectively sewer the new development. Pressure sewers can unlock land that may have otherwise been unserviceable or accelerate the development timeline. Finally, pressure sewers are used to replace existing collection systems. Similar to the septic tank replacement approach, pressure sewers are used where an existing collection system has reached the end of its useful life, or the cost to maintain that system is too great. When comparing the life cycle cost of renewing a gravity system versus the cost of installing a pressure sewer system, the whole of life cost for pressure sewer systems can be often much lower. We'll talk more about system cost later when we talk about life cycle. Beyond the constructability of the pressure sewer system, there are a variety of other benefits. Pressure sewers don't require large, expensive, and critical central infrastructures like traditional major gravity pumping stations or vacuum pumping stations. This reduces cost and defers risk. Debris plagues every wastewater system around the world. Things that are not supposed to be in the sewer system end up in the sewer system. Especially today, we see a lot of baby wipes ending up in sewer systems because of toilet paper shortages and those sorts of things. This is a relevant industry and social problem, and best solved by education of the residents. However, practically speaking, it will never be completely solved. E1 grinder pumps perform well with most types of debris, but when the system is abused due to high amounts of debris, this can create a problem with the grinder pump. However, the problem is nearly always isolated in the pump, not in the pipe network. If it's in the pipe network, it might require expensive excavation and troubleshooting to find out where that blockage is. Repairs are isolated and system abusers can be dealt with directly. Finally, the materials and methods used in pressure sewers result in a sealed system. There's practically zero stormwater infiltration. This reduces costs and risks of overflows during wet weather. Pump systems are generally more intuitive than negative pressure vacuum systems. This means faults are easier to identify, and troubleshooting methods are required for vacuum systems like trial and error. Grinder pump stations are specifically designed to have emergency storage capacity. This allows residents to continue to use water during a power outage or due to a maintenance of a component in the pressure sewer systems. Gravity systems and vacuum systems, which are shared by multiple properties, generally have very little emergency storage and therefore can create higher risks for the operator. Next, as we will discuss in more detail, grinder pumps actively break down debris in the system through the grinder mechanism. Gravity systems usually attempt to allow that debris to pass through until collected in a pump station or treatment plant. Vacuum systems attempt to use high force from differential air pressure to force that debris through the system. Neither of these approaches are very effective and create costly problems in the network. Next, I'm going to briefly review some technical details about E1 products. So if we take a cross-section of an individual property from that earlier image, this is what the typical grinder pump station would look like. The station is typically located within the property boundary. That minimizes the length of the private drainage, which can often be considered as the most vulnerable part of any collection system. The unit shown here represents one of many types of grinder pump stations that E1 manufactures. There are a variety of different configurations and geometries to satisfy operational, regulatory, and logistical needs, but the general operation is identical among models. Wastewater flows into the collection tank. Inside the collection tank, the grinder pump automatically detects when the water level reaches a predetermined level and turns on. The wastewater is macerated and pressurized. Then it's discharged through a small diameter line. At this point, this line is usually 1.25 inches or 40 millimeters outer diameter. There's a valve assembly referred to as a lateral or boundary kit assembly, which features a flapper type non-return valve and an isolation ball valve, as well as a clean out port. The wastewater enters the common main. Again, this common main is typically located in or near the roadway. The diameter of the common main will vary based on the hydraulics of the system, such as number of pumps connected, the pressure in that main, any elevation changes. We'll talk about main sizing when reviewing the design method. As a point of information, it's not uncommon to have a pressure sewer project with hundreds of connections into a common pipe network where the largest diameter is less than 4 inches. The equivalent gravity sewer main for that project would be twice or even 3 times the diameter. The final portion of the system to mention is the alarm panel, which is located on the side of the house or dwelling. All of the level sensing control devices are integrated into the pump itself. Therefore, we typically don't refer to this as a control panel since it doesn't really control the pump. Its primary purpose is to provide a visual and audible alarm if there's a high level in the tank. This alerts the property owner that there is a problem and service may be required. Regardless of the tank configuration, the common element is the grinder pump. The E1 grinder pump, often referred to as the core, can be considered the heart of the system. It is a 1 horsepower or 0.75 kilowatt, 240 volt single phase pump. Unique to E1, this pump features a large diameter grinding device, which delivers best in class performance. E1 utilizes a progressive cavity, positive displacement type pump. This allows this relatively small pump to generate high pressures. The E1 pump is designed into systems up to 185 feet or 56 meters of head. This facilitates uphill and long distance pumping, which enables large pump stations or lift stations, common in gravity systems, to be eliminated. A single E1 pump through an 1.25 inch line can pump nearly 2 miles in a straight line. Increasing that pipe diameter can increase the distance. The longest E1 project I'm aware of pumps nearly 4 miles from a rural village into a wastewater treatment plant near the town. The E1 grinder pump has an integrated design unique to the industry. The level control system and motor controls are incorporated into the pump. The result is an integrated design, which is quick and easy to install and is interchangeable at any site. Finally, the E1 grinder pump is designed with robustness and reliability in mind. Much like other appliances found in your house, The E1 grinder pump does not require any preventative maintenance. It's run to failure, just like your dishwasher or refrigerator. There are wearing items in the pump, and E1 expects these to last on average 10 years in a residential application. This minimizes the operational costs and burden to operate and maintain a system. We'll discuss operation and maintenance in more detail later. The grinding capability of the E1 pump is paramount to performance. As mentioned earlier, operators around the world struggle with debris in wastewater networks. The ultimate solution is social engagement and community education. However, in order to give peace of mind, the E1 design offers best-in-class grinding performance when faced with household items. The large diameter grinder wheel creates a low inlet flow velocity. This causes debris to be gently exposed to the grinding face. Debris is processed through small bites. The result is resistance to blockage or jamming due to the debris. In contrast, other grinder pumps feature a small grinding device which creates high inlet velocity. Debris is rapidly sucked through the grinder, which creates really exciting YouTube videos, but also increases the likelihood of a blockage, especially as the grinder loses the sharp edge. Speaking of a sharp edge, the E1 grinding device does not rely on a sharp edge. It is a true grinder. The low inlet velocity, along with the grinding device, creates that best-in-class performance. The alarm panel provides an audible and visual alarm when a high level occurs. The alarm panel's light illuminates and buzzer sounds. This indicates to the resident that there's a problem with the unit. The resident calls a municipality or service provider to investigate and correct as necessary. E1 also offers cellular telemetry options to provide remote alarms and notification to the service provider. The capacity within the tank provides sufficient storage for residents to continue to use water within reason until a technician arrives. E1's documented mean time of service of 10 years means that in general, this alarm system will only need to operate on average every 10 years. So now that we're all experts on the background of pressure sewers, benefits, key applications, and products, let's see it in action. The first case study examines how E1 pressure sewer system was utilized in a new land development project. Shortly, we'll see an example of a municipal septic to sewer project. E1 has the world's largest catalog of pressure sewer case studies, many of which have been converted into short videos. Make sure you visit the E1 website or enjoy our YouTube channel, E1 Sewer Systems. To review pressure sewer system benefits to builders and developers. Pressure sewers help overcome geotechnical challenges like terrain and poor ground conditions. This can be critical and allow land to be developed that couldn't have been serviced cost effectively with other methods. Pressure sewers are much faster to install than other methods. Smaller diameter materials, shallow installation, and non-critical slope means that the land will be ready sooner. In many cases, pressure sewer systems can help defer costs associated with the sewer system. The developer's contribution may initially only be the pipe network. The cost for a grinder pump station occurs during home construction. Sometimes the cost of the grinder pump station can even be passed along to the builder or buyer of the home. Finally, the environmentally sensitive nature of pressure sewer systems can maintain the natural beauty of the development. The sealed network means no overflows and minimal disruption to any existing vegetation. This case study is the village of Seven Lakes in Nova Scotia, Canada. This development consists of over 600 residents and was initially designed with septic tanks. Integrating the residential properties into the surrounding environment was a key goal of the development. The objective was to blend the residential comforts into the natural surroundings, and this was problematic for the septic tank solution. Deterioration of the septic tanks over time was known, and improper maintenance of the system will risk water quality of the surrounding lakes. The deep trenching and pump stations required for a gravity system would seriously impact the existing environment. In fact, the regional municipality stated that gravity sewers, quote, invariably begin to leak and become conduits for surface and groundwater to enter the collection system. The developer needed a better system in order to be successful. The E1 pressure sewer system was investigated by the developer due to the municipality's encouragement to find a better solution. The system was designed with 2 to 4 inch HDPE mains and grinder pump stations located at each property. Cost per property for the grinder pumps were the equivalent of approximately $5,300, with the developer constructing the rest of the network. The pressure sewer system delivered the architectural flexibility to locate the home anywhere on the lot. Remember, E1 can defy gravity and avoid deep excavation. This enabled the best and most scenic use of the land. The E1 solution provided the developer and homebuyer with a reliable and environmentally friendly solution. We'll have another case study later, but now let's learn how pressure sewers are designed and how E1 can help. The first step in any design process is to collect information. This is a critical step since, like most things in life, the quality of the output of the design is a function of the quality and accuracy of the input. The next step is to break the project site into small segments or zones. Each zone is examined separately, and then the analysis considers how the zones operate together. The total dynamic head, or TDH calculation, is performed to ensure the grinder pumps can operate within the network given friction losses and elevation changes. The network pipe sizing is selected and modified to ensure a sufficient flow velocity is achieved and to minimize the retention time in the pipe. The best news is that most of these calculations and modifications are easily performed using a free tool called the E1 Design Assistant. So the keys to his design: first, gathering the project details are critical. As listed on this slide, the key inputs are a layout of the area to be served, usually showing individual lots or properties. Typically, we like to work from AutoCAD layouts of properties, but we can work from PDFs, given there's a graphical scale, so we can accurately measure pumping distance. A general estimate of the sewage flow per property is required. This can be based on generally the occupancy or maybe regulatory constraints. The pipe type generally accepted is to use HDPE SDR11, but other pipe types are acceptable. We also require topographical information for the areas, so we know if there are any hills that need to be pumped over. The discharge location of the system and the type of discharge is needed. We need to know where the system will go. This can be into an existing collection system like a manhole or a pump station, or all the way to a new or existing treatment plant. Pressure sewer systems can also discharge into pressure mains, depending on the pressure within that main and the pressures within the pressure sewer system. In addition, any other codes or regulation, climate information as well is utilized within that design process. I've talked about discharge locations, and I don't need to read all the different options here, but it's important to know what discharge type and condition that we're discharging into. The E1 design method is referred to as the probability method. This method is based on a statistical model developed from empirical data. It shows that given a total number of pumps, there will be a statistical maximum number of pumps operating simultaneously. This statistical model is what creates the table shown on this slide. It's called the maximum number of simultaneous operations table. So, given the number of pumps in the left-hand column, the statistical model tells us how many of those pumps will be operating simultaneously. So if there are 100 pumps, we look at the row 81 to 113, and the table and the model tells us that there will be 8 pumps operating simultaneously. Another critical assumption and element of the E1 design approach is a constant flow rate from each pump. The positive displacement pump delivers an essentially consistent flow rate regardless of the system pressure. This allows for a linear relationship between the number of simultaneous operations and the overall flow rate. So back to our example. If there are 100 pumps, 8 will be operating simultaneously, and the flow rate of each pump is approximately 11 gallons per minute. That means I know the flow rate through the network will be, that's right, I hope all of you yelled 88 gallons per minute at your computer screen. This becomes the basis for other calculations like velocity and total dynamic head. So now we have our project information and understand the assumptions. We can begin the design process. And the best way to understand the design process is through an example. So that's what we're going to review. The process is essentially 2 phases. First, it's the procedure of taking the layout and creating zone designation. Within each zone, we will record the number of pumps, zone length, and maximum main elevation. The second phase is to input the data into our Design Assistant tool. This tool performs the calculation and an optimization to output recommended pipe sizing. This left screen shows the output of calculated flow velocity and total dynamic head, and the right is the calculated retention time. So again, the best way to learn is by doing. So let's look at an example. This is a representation of a coastal development with connections located on various roads. For simplicity, let's call this Derrick Estates. The discharge point is marked towards the upper right. Each property is represented by an open circle. The small line connecting the circle to the main is a representation of that 1.25" or 40mm pipe between the grinder pump and the main. The hydraulic losses through that pipe are generally considered to be negligible in our assumptions. Generally, the E1 assumptions are conservative enough to absorb the minor losses from that section of pipe, as well as any friction loss through fittings and direction changes, so on and so forth. As described before, the first step is to create zone divisions. The E1 method creates a zone division whenever the expected flow changes. This will occur when more simultaneous operations occur. For example, when we go from the quantity of pumps that will have 2 simultaneous operations due to a total number of pumps of 3 to 3 simultaneous operations due to a total number of pumps of 9. Also, the flow will change when a branch joins the main line. So branch junctions are also points where zone divisions occur. The best practice is to start zone designations at a point farthest from the discharge. Also, the flow should only move in one direction. Do not loop pressure sewer mains. This will ensure the flow always travels in one direction and we don't have any dead zones in the main. Finally, just for clarity, a zone change does not necessarily mean that the pipe diameter will be different. It's simply a designation. So generally the first zone is the simplest. We usually skip the first row. I didn't do great in statistics, but I do know enough that if there's a total of 1 pump connected, that the maximum number of pumps that can operate simultaneously is 1. But just for efficiency's sake, we typically start at the second row in our simultaneous operations table. So it's fairly common that the first zone in most E1 pressure sewer designs will be 3 pumps. And you'll see them marked here, 1, 2, and 3. The black arrows on my layout are kind of, we're kind of cheating here, but those are going to show you where the zone designations are going to be. They're also indicating direction of flow. So there's my first zone. Zone 1 is 1, 2, 3 pumps. The next zone in this example will be where the total number of pumps reaches the next point on that simultaneous operations table. So we'll look at this 4 to 9 range. And again, we generally look for optimization. So we're going to look for as many pumps as possible within that zone. So we already had 3 pumps in the previous zone. So in order to get to 9, we need 6 more pumps. 4, 5, 6, 7, 8, 9, and that arrow indicates my zone division. These 6 pumps create zone 2. Again, referring to the simultaneous operations table, the flow changes when we hit a total of 18 pumps. So we need 9 more pumps, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now we reach a branch. A dead-end branch like this means we don't have any upstream pumps. So we start again from the simultaneous operations chart. So even though these are marked as 19, 20, and 21, in our design, this will be shown as a new branch. So 1, 2, 3, and we have a zone division. Now we have a zone division for 2 reasons. We've reached our simultaneous operations and we have a branch junction. Continuing just downstream of that junction, we have a total of 21 upstream pumps. If you remember, we had 18 from this longer main and another 3 coming from this branch. So now we start at 21 and we look at our simultaneous operations chart. 21 is somewhere in this 19 to 30 range. So we need to try to get all the way to that 30 to be as efficient as possible. So 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and there's my last zone division. The zone designation process is fairly straightforward once you understand how this process works. For the sake of time, We're not measuring and recording zone length, but that information would be required when we're inputting data in the design assistant tool. Also, we're not capturing any topographical information. In each zone, we'll record the lowest approximate location of each pump and the maximum main elevation. Once we have all the relevant information, we can begin to input the information into the design assistant software. Initially, some project-specific information is recorded. Perhaps the most important point to check on the screen is to select the system of measurement and the power of the system. It's 50 or 60 hertz. The power frequency does affect rotation speed on a single phase motor, which in turn slightly modifies the flow rate. The zone information tab, this is where we input all the information that we were just capturing. We'll see zone designation numbers. The next column is connects to. This is telling the software which zone number 1 pumps to. So if you follow along, that first zone was pumping to the second zone, and that second zone pumping to the third zone, so on. Pumps in zone column is just that. It's capturing those pumps in zone. Again, if you remember 3, 6, 9. 3 again, because we had that small branch connection that joined the rest of the network. Maximum flow rate per pump. Now, I'll say this example is in metric units, but if we would have selected imperial units, flow rates and all the other measurements would be in the relevant imperial units. But flow rate, this will either provide a default level or you can manually enter a flow rate into this column. Liters per day per dwelling is going to be utilized in our retention calculation. And again, this can be based on project-specific information, regulatory drivers. Zone length, again, pretty straightforward. This is in meters, and maximum main elevation and minimum pump elevation. So these are the inputs into the design assistant software. Once we have our zone designation and have input our information, this is where the magic happens. This is where we can now select our next tab called Design Page 2. Let's see what that looks like. So once that zone information is entered, Design Page 1 computes the total dynamic head for each zone based on upstream and downstream flows. The software provides a recommended or baseline pipe diameter for each zone. So we'll see now we have pipe size that's been optimized. We'll also have calculations for maximum velocity and a variety of incremental calculations, but then ultimately total dynamic head. The software uses the modified Hazen-Williams formula to calculate friction loss, really just due to simplicity. Other methods are used in industry, but most pipe manufacturers publish pipe roughness or C factors, and this calculation provides an acceptable level of accuracy. On Design Page 2, this provides the accumulated retention time measured in hours. This information provides general guidance. Retention time should be minimized. The longer the retention time, the higher the risk of the discharging sewer might be septic and cause, say, odor complaints. Sometimes there's nothing you can do about retention time. The distance of pumping, the number of connections might require or might result in longer retention times. But this can provide, like I said, guidance. If the discharge location doesn't have odor control measures and is in a residential area, then the guidance could be that part of the project is to install odor control measures. Likewise, if the discharge is into the headworks of a treatment plant, the odor control, corrosion control measures are likely already there, as well as the effects of dilution. On either design sheet, the software allows the user to modify the pipe sizing from the drop-down menu. Upon changing the pipe size, the software automatically recalculates the fields. Pipe sizing seeks to achieve a balance between the 3 key elements: total dynamic head, flow velocity, and retention time. For TDH, our objective is to remain below 185 feet or 56 meters, where lower is better. Lower TDH reduces the low on wear and tear on the pump and prolongs the service life. Flow velocity is what helps to ensure that any solids in the slurry remain in suspension and buildup on the wall of the pipe is cleaned. This is often referred to as self-scouring, and the industry accepts minimal velocity of 2 feet per second or 0.6 meters per second. Finally, as discussed, we want to minimize retention time. Acceptable retention time varies from region to region. When modifying pipe sizing, the software will recalculate any values which are below the recommended thresholds and conditionally highlight those in red, as shown here on these 2 slides. In the top image, this is velocity. So what's likely happened is these pipe sizes have been increased and therefore decreasing the velocity through those zones. In contrast, this lower image shows TDH. So likewise, what happened in this case is those pipe sizes were reduced, therefore creating a lot of extra load or demand on that pump. Besides the technical objectives, pipe sizing can also be modified for, say, regulatory or logistics reasons. There might be a requirement for a minimum pipe diameter through a certain area, like under a roadway or under railroad tracks. Also commercial reasons, maybe certain pipe diameters may not be readily available. The flexibility of the software allows the designer or engineer to essentially modify the network to evaluate the impact of those changes. For example, the installing contractor says that a 3-inch pipe or the fittings are in short supply, and can they use the 2.5-inch that they already have? We can quickly and easily model that and see what the consequence is. So the second case study I wanted to review to you is a municipal or septic tank replacement project. One of the key benefits to a municipality or an operator is the sealed and resilient pipe network, especially when compared to gravity and vacuum systems. HDPE pipe network is resilient to inflow and infiltration of groundwater and stormwater. That I&I strains infrastructure, increases operational costs, increases the risk of a sewer overflow. Vacuum systems often advertise themselves as sealed systems as well, but many projects around the world have shown that due to the design, materials used, or construction, that isn't always the case. Additionally, if I&I does enter the vacuum system, it can disrupt the air-water mixture that the system relies on to transport the wastewater. When this happens, the system is considered waterlogged and can essentially shut down just because I&I at a single valve. If I&I enters the grinder pump system, usually at the grinder pump station, and usually because of damage or defect in private drainage, the primary consequence is additional run on the pump. While this does increase the operational cost of that unit, it doesn't shut down the system. Also, sources of I&I in a pressure sewer system can be easily identified by surveying pump run times. Pressure sewer systems can be deployed in established residential areas with minimal disruption. Installation of the pipe network with directional drilling is quick and leaves very little trace. In the event directional drilling cannot be used, shallow depth and no grade means trenching is quick. Finally, pressure sewers allow the municipality to sewer an area that has geotechnical challenges. Poor ground conditions like rock or running sands, high water table and coastal areas are overcome with that low impact pipe network. The high head capability of the grinder pump helps to overcome the topographical issues that require large pump stations for gravity networks or are impossible for vacuum systems which have limited static lift capability. This municipal case study is in Washington State. The project was a coastal area comprised of 350 residential properties, which were served by septic tanks. Water quality monitoring of the area was beginning to show public health risks. In fact, the health district had declared a health hazard for the area. Something needed to be done. For this project, the local municipality structured the solution was to be funded by the property owners, since they would be receiving the benefit from the system. In order to deliver best value for money, the municipality cast a wide net and considered a variety of options. This included gravity, pressure sewer with grinder pumps, and a step system, which is a septic tank effluent pumping system. During design and option evaluation, estimated capital and estimated operational costs were collected. For operational costs, similar systems were surveyed and average values were determined. The table on this slide shows the high-level comparison of the capital and operational expense for each option. The pressure sewer or grinder pump system provided the best performance and value. This project was installed in 1999, so it's well over 20 years old now. The most recent data have revealed the cost to operate and maintain the system is actually much lower than originally estimated. Key metrics here are the mean time between service call, MTBSC, and cost per station per year. And from an environmental perspective, progressive water quality measurements have shown a positive impact on the water quality and resolved the health hazards. A special plug for the E1 catalog of video case studies. Check out the E1 website or visit the E1 Sewer Systems YouTube page for a collection of beautiful and compelling case studies. I guarantee you will learn something new and see something you like. My personal favorite was the quote from one of the utility managers who said, "Who was stupid enough to install 2,000 pumps?" But by the end, he directs his engineering staff to avoid gravity and now only installs E1 pressure sewers. What a roller coaster of emotion with a happy ending. So let's briefly discuss the construction of a pressure sewer system. Typically, I like to look at a pressure sewer system in two general phases: the off-property work, which is the HDPE pipe network, valves, fittings, etc., usually installed in public property or utility corridor right-of-way. On-property portion deals with the installation of the grinder pump station and alarm panel. In most cases, the grinder pump station is located within the private property to minimize the length of that private drainage and simplify the electrical connection. Off-property construction begins with system piping. Historically, a variety of materials were used, but anymore, HDPE is by far the most common, with SDR being the most common size ratio. There are a variety of pipe diameters commonly produced, with small diameters typically produced in coils and large diameters available in straight lengths. Assembly is with either mechanical compression fittings or electrofusion methods. The pipe network can be completed using open trench methods, which is common with, like, say, new development where other services are being installed, or trenchless methods like directional drilling, which is more common with a septic to sewer program when you're working in an established area, minimizes construction and restoration costs. Variety of other valves and devices can be found in the pressure sewer network. Flushing connections are recommended at points where the mains can be clean with the injection of high volumes of water. Diagram here is a general layout from E1, typically assembled by the installing contractor using approved components. And E1 generally recommends flushing connections are installed at branch connections in every 1,000 feet, or say 300 meters. Division valves are also commonly found in pressure sewer networks. Type of valve and placement generally follows local requirements. Division valves are incorporated in flushing connections, so commonly you'll find the two of them together. Division valves provide a mean for system isolation and to facilitate maintenance activities like repairs or adding new connections. The nature of a progressive cavity pump it's used in E1 means that the pump can move trapped air through the network. This is something other pumps like centrifugal pumps struggle with. Air will be introduced in the system at each pump cycle. As air accumulates, it can add resistance to flow, which increases the load on the pump. To relieve the extra load, air release valves are recommended at high points and where there is a change in elevation. These devices allow air to escape. Similarly, vacuum release valves are used before downhill runs to prevent any damage due to negative pressures. The on-property installation is fairly straightforward: locate, excavate, install, connect, bury. Grinder pump station should be located in a position where the aesthetics of the cover can be integrated into the existing or new surroundings. The cover of the station must be accessible and exposed, but are often located in landscaped areas. Alarm panel is located within line of sight of the grinder pump. Installing an E1 station is not difficult. In fact, we've purposely designed it to be easy. But E1 has learned that system reliability is a function of the quality of the installation. E1 has installation instructions, installation overview videos, again, check out YouTube, and a certified installation program. System operation and maintenance is often a source of uncertainty and doubt to those new to pressure sewers. Faced with the potential of many pumps, people believe that the cost and manpower needed to maintain the network is immense. However, that is a myth that E1 strives to dispel. This section, we will review some of the basics and expectations of operation and maintenance of the system. E1 equipment is purpose-built to be as serviceable as possible. The E1 core integrates the grinder pump, level control, motor controls into a modular unit, easy to install and replace. Electrical connection between the grinder pump and the panel is with a large purpose-built quick disconnect plug. This creates a simple and reliable means to disconnect the power to the pump without the need of tools or specialized training. Stainless steel components are more robust than PVC equivalents. And finally, the design of the alarm panel versus a control panel means all the critical components for the pump are protected from the environment. And also, if a fault in the panel were to occur, it doesn't mean the pump will stop to operate. That reduces risk. Reliability is key to E1, and that's why we thoroughly and continually validate the product to ensure it is as robust as possible. Any new products or modifications to existing products are rigorously tested in live sewage, as well as through a life cycle test lab, which can mimic long-term operation in a short period of time. It's not uncommon to validate designs through hundreds of thousands of cycles in-house before even conducting field trials and ultimately releasing for production. E1 has a variety of tools and trainings designed to aid in the operation and maintenance of the equipment. O&M models vary by project, and E1 and local distributors help to develop a plan that works best for a particular project. And when we examine operation and maintenance costs, two key metrics are mean time between service and cost per pump per year, like I talked about with that Beach Drive example. Cost per pump per year is fairly straightforward calculation, total expenditure divided by the number of pumps. The mean time between service call calculation can be applied over a long period of time to see, on average, how frequently each pump needs to be serviced. This slide shows some examples of data collection on the operation of systems. E1 generally expects cost per pump to be less than $50 and MTBFC in that 10-year range. These numbers are for properly installed and operated systems. Systems which are subjected to, say, a lot of abuse will and can have higher costs, and E1 actively gets involved to provide support to projects like that. And we've had a lot of success working with users to educate the community, refine operations practice, correct installation defaults. As stated really early on, we rely on every system to be successful since our reputation is at stake. Our operational data comes from sources all over the world. We have the longest and largest installation base in North America, but there are significant installs in other continents. Data drive our performance and reliability claims. The final section is how we assign a life cycle cost to pressure sewers and other options with the goal of determining which is the best solution for a particular project. So first, we must understand what a life cycle analysis actually is. It's really just a financial model used to compare alternatives. The financial model must not only include today's cost, usually the construction cost, but also tomorrow's cost, the cost to operate and maintain the system throughout its practical life. This long-term assessment provides the user with a better understanding of what to expect throughout the life of the asset. We created the Lifecycle Cost Calculator tool to address many of the myths and misconceptions we receive about our technology and about others. For example, it's common to hear that gravity systems are free to operate. This is simply not the case. And the Lifecycle Cost Calculator tool has specific prompts to guide the user to include all those costs for things like root infiltration, electricity costs at pump stations, etc. Vacuum systems commonly make a lot of the same claims as pressure sewers, that they're sealed. While this might be true on some systems and others it's not. The number of pipe fittings in a vacuum system is often 10 times the number of fittings on a pressure sewer system, and each one of those fittings is a potential leak point. Also, the extreme high velocity in a vacuum sewer network can cause debris to rupture the pipe at points of sharp direction changes. And once a leak begins to occur, the process of troubleshooting and finding that can be very difficult. For pressure sewer systems, common misconceptions we receive are that they're maintenance intensive. As covered in the operation and maintenance portion, a properly installed and operated system is often less expensive to operate. We continue to fight the perception that all pumps and pump stations are created equal. And the cost and criticality to repair a grinder pump station in a pressure sewer network is the same as a large major pump station. That's simply not the case. The risk, cost, and complexity of maintaining a grinder pump station is nowhere near what it is on a major pumping station. So E1 has created a lifecycle cost calculator tool to assist you in making these assumptions. This tool uses industry accepted practices and has no biases. We have seen projects where the result has been that a gravity system offers a better lifecycle cost, and that's okay. Our fundamental objective is to provide an aid to ensure that pressure sewers are considered and evaluated based on actual merits instead of being disqualified because of the myths and misconceptions. This tool outputs a present worth of the options for comparison, which is the current worth of a future sum of money. Essentially, lower the number, lower the whole of life costs. This is the results page from the lifecycle calculator. In this example, the pressure sewer present worth was about 3.3 million versus the gravity present worth of about 4.4. Again, the purpose of this tool is to aid the user in the evaluation of different options and ensure that proper consideration is given to real operational costs for the different options, not assumptions like gravity's free. Pressure sewer is not always the best option. Every project's different. The best part is that there's no risk in using this tool or the E1 Design Assistant tool. Both are free from E1. Well, congratulations, everyone. We made it to the end. If you can't tell, I'm extremely passionate about what we do. I believe pressure sewers are an excellent tool and offer a high level of value. Our systems solve challenging problems and improve environmental quality of life. We purposely design our products to be easy to design, install, and operate. We will work to earn your trust and become your trusted advisor. And before I hand it over to Rachel for some Q&A, I wanted to offer our help in your next project. Contact us if you want to discuss something in more detail, download any of the tools I discussed, or perhaps arrange a follow-up meeting with others in your organization. Thanks.
Derek, thanks for that excellent and passionate presentation. So as promised, everyone, we'll start right in on our Q&A session. Derek, are you ready for a little speed round?
Just taking a drink of water.
Okay, very good. I think interior grinder pumps can be installed. Please comment.
Yeah, that's you know, I kind of only really had time to talk about kind of the general makeup of a grinder pump station, but we have a variety of grinder pump stations which are located inside of a house. Actually, way back at the beginning of my presentation, I had a picture of the founding father of pressure sewer, Paul Farrell, and it actually had a grinder pump station. The original grinder pump station was for use inside of a house.
That's right.
We have units called IDUs, or indoor units, that are kind of self-contained stations that can sit directly on a slab or be buried within a slab. And also, if you saw some of those tanks, we have our primary tank is this corrugated design, and we have versions of that are meant to sit inside of the house. Really regional driven about what regions like those indoor units. We see a lot of them in New England, of the U.S. and kind of that East Coast area, where if it's inside, it's protected from the environment and things like that. But absolutely, that's a configuration available.
Okay, and here's a question from Maria. If there is a commercial pump in the design, how do you incorporate this into the design application?
Yeah, so that's something that we've seen over the last 50 years. You know, the concept of pressure sewers were originally designed as a residential solution. Well, kind of it's been application creep, or we've seen our products. It's been interesting seeing our products utilized in new and novel ways. Something that happened probably early on was, you know, we'd have a residential development, say it's 200 houses, but then there'd be a school or a church or some shops in that same development. And it was really compelling, you know, that commercial area or that higher flow site needed to be serviced in the same area. Our general approach is to utilize the same E1 1 horsepower pump, but depending on the flow, we will utilize multiple of those pumps into a common basin. And again, kind of you can visit our website and see a variety of different configurations. Really, there's a lot of standard out there, but then there's also a lot of custom out there. From a design standpoint, we typically represent those systems. It really depends on what the operational configuration is. So for simplicity's sake, say we have a duplex, which is a 2-pump unit, or a quadplex, which is a 4-pump unit. In both of those applications, the general theory of operation is that only one pump is considered in duty. So when we represent that in the design phase, it still only represents one pump. Likewise, when we're looking at, say, a quadplex, then generally the theory of operation is that 2 pumps are in duty. A quadplex can, in a lot of cases, can be considered 2 duplexes in a common basin. So we'd have 2 pumps. So when we're doing our pump count to find our simultaneous operations, like a duplex would be a single pump, and a quadplex would be single pump, and a quadplex would be 2 pumps.
Gotcha. Okay, Colin says, what performance issues occur in oversized pipes when there is a significant delay in 100% build out, or if the project is constructed in phases? Yeah, so
what can be seen is, say we have a master plan subdivision for 1,000 houses. At the discharge point, say, you know, we might have a 6-inch pipe because of the hydraulics for all those. But at some point, someone's got to build that first house. And what you can end up with is essentially low scouring velocity at those larger pipe diameters. There's a couple of different ways to address that. You know, one is understanding, okay, what is the projected build out? We talked about the inclusion of flushing devices inside of it. So it could be that during initial phases of a project, there is a periodic flushing regime. The developer, the operator, something like that, flushes that network periodically. Another potential solution that we've seen periodically is running dual mains. So you might have that 1,000 lots, 6-inch pipe for the 1,000 lots. That's ultimate build out, but for the first 5 years, 3 years or something like that, you may be able to get away with a 3-inch line. So what you'll see is a 3-inch line installed next to that 6-inch line with valve arrangements at some point where once build out reaches a certain threshold, the valves can be opened. You either run them in parallel or you switch all flow over to that larger pipe. The one thing I'll say out there, I didn't specifically talk about it in the presentation, but another real benefit of a progressive cavity pump is it's going to continue to generate flow. So even in those scenarios, say where we have low flow and we start to maybe allow solids to fall out of suspension and build up on the pipe, what's effectively happening in that pipe is we're reducing the cross-sectional area of that pipe, and the velocity through that pipe reduction is increasing. So while in the kind of the native state, that again, that 6-inch pipe, we might not reach that 2 feet per second realm, but after a while, if buildup does continue to occur, that progressive cavity pump will continue to force the same flow rate through there and ultimately reach that flushing velocity.
Okay, and thank you, Derek. Dan asked, with steep downhill grades but heavy ledge area, we are looking into E1 for controlled discharge and ease of installation. Are there special concerns for this type of design?
So downhill pumping is something that a progressive cavity pump, again, is capable of doing. Again, when you talk about other pump types, specifically centrifugal pumps, long downhill sections can create you can create overloads and cavitation of that pump and create a lot of bad situations. So a progressive cavity pump can pump downhill. And some people call this forced gravity, which I kind of like that concept. You know, there's kind of the two key things that the guidance that I would provide, just I guess, without more information, are, you know, a air control before that long downhill run. We'll want some sort of vacuum, air vacuum release valve at the top of that hill. And the other one is when we look at static head, when we look at those different pump elevations, it's incorrect practice to, and no one can see my air quotes, but take credit for that downhill pumping. We can't have negative head. It actually ends up potentially violating one of the laws of thermodynamics, which we generally avoid doing. So what I'll say is don't assume any static head in those cases. We'll have the static head be zero in those large downhill pumping cases. But that's an excellent example. If we've got something on the go right now, we'd love to take that offline and learn more about that project.
Perfect. John asks, does the software allow setting of a minimum velocity? So I believe he's referring to Design Assistant.
So the software is going to initially output optimized pipe sizing. It's going to give you basically the lowest TDH that will have acceptable flushing velocity. So it won't, if you want to, you can override it and have it choose a larger pipe size and have that velocity drop below your 2 feet per second, 0.6 meters per second, whatever unit you're working in. It'll conditionally format that red. It'll tell you there's a problem. It's not physically going to stop you from making that choice, but it will identify to you that, hey, this doesn't look quite right. Maybe take another look at that.
Okay, and I think we have a few more questions here. How do you convince municipalities to accept these systems over the conventional gravity systems?
That's a very nuanced question. It's you know, it's one of those things that we E1 that's one of our primary objectives, is to remove or reduce a lot of the fear, uncertainty, and doubt that come with these systems. We oftentimes try to understand what their current challenges are. You know, where are you struggling right now? I've been involved with projects around the world, and I can pretty much guarantee that every municipality will say, we've inflow and infiltration into our network. We've got issues with debris, baby wipes into our network. You know, we don't have enough money to replace all these septic tanks or continue to spend money on these systems. So uncovering what their core needs are and what their core objectives are, and then one by one addressing what those different concerns are. I'll also say that I've never successfully walked into a municipality once and convinced them. It usually does take a series of interactions, leveraging a lot of the E1 case studies, a lot of the E1 data. The municipality doesn't have to believe what some smooth talking salesman tells them. They can do their own investigation. They can talk to E1 references. They can look at the data themselves to help justify those answers. But that approaching municipalities, that's something that E1 and our distributors are more than happy to help you, whatever your role is, help you either shoulder to shoulder in that meeting or develop a compelling case to demonstrate to the municipality why this is a superior system.
Well, thank you, Derek. Unfortunately, it looks like we're just about out of time here. I think we had so many questions that we didn't get a chance to answer. We'll be following up in an email with answers to those questions. I think, Derek, we're going to have to do some kind of live Q&A session with E1's Director of Engineering and just, I mean, seriously, we've had such great feedback. So on behalf of all of us at E1, we thank you for joining today's session, and we really do look forward to seeing you soon. Be well, everyone, and thank you.